Rust, the language behind Firefox, Discord, and half of modern infrastructure. Famous for being fast and safe, and famous for being extremely hard. In the next hour, we're going to fix that from your first line to the concepts that scare everyone, including ownership, borrowing, trades, all of it. We're going to do it hands-on. Let's go. So obviously the first logical step is we're going to start by installing Rust. So head on over to rustup.rs, and if it's automatically going to detect your system, and all I'm going to do is I'm going to open PowerShell. So this is my PowerShell. You can open up command prompt or anything, and I'm going to copy this command and I'm going to paste it right here, and I'm going to press enter, and it's going to start this installation. You can also use the GUI version, the exe file, but I prefer the CLI version. And when prompted, just go with default installation. So you don't need to do anything, just hit enter if you're on the screen. Oops, actually, I believe you need to hit 1. So just hit enter. I put an accidental hash on top. All right, now it's automatically going to download everything for you. Okay, so sometimes your Rust installation might get stuck after Rust fmt. Just hit Control-C. And let's clear this out, and I'll open up a brand new PowerShell. And when you do that, if you type rust c -- version, and if it shows a compatible version installed, like it does right here, you're good to go. So that one command basically installed Rust and Cargo. So Rust and Cargo are two things that we need. Cargo is basically like the building packager for your Rust applications, and we're done now. So you must have something later than 1.9 something, and Cargo should be of the same version. So right after that, we're going to move on to our IDE. My preferred IDE of choice is actually Rust Rover. So this is from JetBrains IntelliJ. It's a really good IDE, really powerful, saves you a lot of time with a lot of debugging features. But I know a lot of you love to use Visual Studio Code as well. So you can either get Visual Studio Code with this extension. So you can look at this tutorial, which will also be linked in the description. So basically, docs languages Rust, and you can install these extensions and follow through these steps to set it up on your Visual Studio Code. And throughout this series, I'll be using JetBrains itself, but I will reference for all of those out there who are using Visual Studio Code all of the commands that if anything needs to be specific. So simply download this, and after you do that, you should have Rust Rover installed. So I'm simply going to open up my version of Rust Rover. So right here, you'll have this section. And in this section, all I'm going to do is I'm going to create a new project. I'm going to select the location. So basically like so. And your toolchain location should be highlighted by default. C users LOQ or like whatever your user is, and then cargo/bin. If this is not, then you might want to go and find that path. Your toolchain version is automatically detected as well. And your environment variables, everything else should be the same. Just leave this to binary and then hit create. So we were at Rust Rover right here. On the welcome screen, click on new project, and in the dialog box, confirm that it's binary and set the project name to just something really simple. So right here inside Rust, I'm going to set it to something like hello_Rust and leave everything as default and click on create. So Rust Rover creates some files for us. And for those people who are using VS Code, simply open up your terminal anywhere. So like you can open up a command prompt in the folder and simply just go cargo new and then type in your new project name. So I'll just leave this empty for now. So you actually put in a value. So you put in a value right there and it will create a new folder for you, and you should have all of these things. So Rust Rover creates a scaffold and a working project for us. The files that matter right now are inside src. We have main.rs and cargo.toml. So both of these should be open by default if you're using Rust Rover. Cargo.toml is the project's config file where you have your name, your version, and any external libraries under dependencies that we add later. And these are actually called crates, and we won't touch this yet. All right, so inside main.rs, we have fn main. Every Rust program starts running inside a function called main, most likely like other programming languages as well. And inside it, we have println with an exclamation mark, which basically, if you hover over it, you can see that it says a bunch of text, but in shortcut, that exclamation mark means that this isn't a normal function. It's macro. Macro in Rust basically means a code that writes more code for us. So println is something that writes to our terminal. That's why it's a macro. That's why it has an exclamation mark. and we'll dwell on that more later on. So let's edit the string to say something for us. So hello Coding, for example, and then let's run this program. So if you're on VS Code, then you might have to run this differently. But if you're on IntelliJ Rust Rover right now, just hit run on top. You can run this, you can hit run over here, you can debug over here. But since most of you would be using VS Code, I'll do it from the terminal. Just remember, you can hit this run at any time. So in the terminal, just simply type cargo run. A side note is sometimes you might get something like this. It might say, please ensure Visual Studio 2017 later is installed, and it's going to say could not compile hello Rust. So all you need to do is you need to go to your browser. So I'll open up my browser right here. And the original website that we visited, there is a text that says you may need to install Visual Studio prerequisites. So simply click on this link and it'll take you to this website or this documentation and follow along. In short, what you need to do is just copy this winget command and then run it in your terminal, which I am running right now. Okay, so in GUI, you should get this screen now. Let's look at the documentation. So it says select the desktop development with C++ load. So I will select that. So I have it right here. I'm going to click on install. Actually, I want to change this file location. I want it to go inside my D drive, actually. And I'll change that to be under my D drive. And that's fine. And I will click on install. And it's going to start that operation. Okay, we're done with the Visual Studio installer. This might have taken some time. Right after doing all of that, everything should be up to date and you can successfully close out of it. If it asks you to install anything else, if you're on extra language packs or something like that, you can go ahead and do those. But once you're finished, you can go continue installing Rust. Since we've already installed Rust, it says successfully installed right here, and we've installed it right there. Simply going to open Rust Rover. Let's clear this out and open up a new terminal. So close your previous one, open up a brand new terminal, and then we're going to run cargo run again. So cargo run, all it does is it does two things under the hood. So the first thing is it builds your code. So you can see that it's compiling your code, and then it runs in one shot. And there we go, we get hello coding. So all compiled and run in one command. All right, so let's start. We're at this point already. The thing that we're going to be doing is we're going to be doing inside main.rs. So in VS Code or in Rust or anywhere, it's going to be exactly the same from now on. So we're going to clear everything and we're going to add our main function right here, like so. And we're going to declare some variables. So let x equals to 5, basic way of declaring a variable, and print ln exclamation mark. X is, or actually inside quotations, x is brackets, and we can give an x right there. So what this does is, actually, I'll disable my inline AI suggestions, just that it's a bit easier for me to explain things. You can leave this on or disable it if you find it annoying, but I'll disable it for now. So this is pretty simple. Let x equals to 5 declares a variable. In Rust, variables are immutable by default. So immutable variable means cannot be changed after set. And println, okay, so this is println with this. So curly brace is a placeholder. Just remember, curly braces are placeholders. So whatever variable you pass after a comma will be replaced. So this placeholder is going to be replaced by it. So if you run this now, I'm going to go inside the terminal and cargo run. It's going to say x is 5. So below it, let's try actually reassigning this and trying to break it like so. So x equals to 6. And we're going to do this, and we're going to try to print ln again. So print ln x is like so. Now, immediately you can see that your IDE shows a red squiggle under x equals 6 even before running. And if you hover over it, or if you actually click on this line and hover over it, it shows cannot assign a new value to an immutable variable more than once. We're going to try to run it anyways to see the actual error that we get. So cargo run would give us expected this, but found x. So, okay, we actually need to give in an ending to that statement. And let's run that again. So we get this. Cannot assign twice to an immutable variable, and clearly you can see the compiler output doesn't support changing of variables. It's telling us plainly you never said this could change. So we have to actually say that x can change to be able to change x later on. We didn't say that, so it doesn't let us. In Rust, this is caught immediately, whereas in other programming languages, it may not. This is a teaching gift that Rust gives you. and it's pretty handy on so that you can find changes pretty early on. But what do you do if you actually want to change this variable? So right here, it's not letting us change x to 6, but if we simply type the keyword mute like so, it's now going to make this variable mutable. So instead of immutable, it's now a mutable variable, and it can be changed after set. So if we simply run it now, cargo run, we can see x is 5 and x is 6. Okay, next let's look at some constants. So right above fn main, we declare our constants package level. So right outside of any functions. So I'm going to define a const max points. I'm going to give it a type of u32, and I'm going to give it, for example, 100 underscore 3 zeros. Okay, what is this line? This is a constant. Constant is always immutable. So you cannot do something like const and then write mute right here, because constants are always supposed to be immutable. They cannot be mutable, or they cannot be changed. Always immutable, and a type is required. Type is always required for constants. So here we're using the type u32, and by the way, this is how you declare types. So you write the variable name and you give it in a small colon and then write in the type. So u32 basically means unsigned. Unsigned basically means this cannot be positive or negative. It's always positive, so it doesn't have a negative, and it's a 32-bit integer. And by convention, Rust constants, so convention means like you always want to follow this convention, are screaming snake case. So always capital letters separated by underscores, like so. An interesting property in Rust is actually shadowing. So shadowing, some people find this difficult, so I'm going to explain it very simply. So let y equals to 5, right? Right after let y equals to 5, if I print ln the value of y, so y is, and then print this value right here. And if we go into our terminal and simply go cargo run, you can see that, oh, we actually need a semicolon. So make sure to add semicolons after all of your statements. Don't forget about that. We'll learn the importance of that as well. So is dead code. Oh, also, by the way, it warns you about that. So you can see that constant max points is never used. So if you've declared any variables inside Rust and then you've not used those variables, your program is going to throw a warning during compile time. It doesn't actually stop your program from running at all. It proceeds to run your program anyways, but it gives you a warning. So we can see x is 5, x is 6, and we can see that we printed y is 5 right here. There's a few ways we can change this y, the value of y, without making this mutable. For example, if we do something like let y equals to y plus 1, we can actually do this. And print ln y is, let's go y. You can actually see that change. It won't actually give you a compile time error. It will actually change the value of y. Similarly, you can do stuff like let y equals to y times 2. So any operation of the variable in itself is permitted. And if you go into a terminal and then run it again, you can see that we got y plus 1 times 2. So 6 times 2 will be 12. So this is called shadowing. I can reuse let. In this method, I use reuse let to create a brand new variable. So this is actually a new variable that uses the value of the old y. Each value here is a fresh variable and not a mutation. So this y is different to this y. This is a completely new value for y. As soon as I declare it again, this y can never be used again. It lets me transform a value step by step without ever needing mute. So this is another way to change your values. Okay, now the core of every programming language, let's look at some data types. So I'm going to cut out this line right here, and I'm just going to start with my fn main and nothing else. And there's a few data types that we have. Let's look at scalar data types first. So for an age, you'd use something like u32 and then type in an age like 18. So Rust has a small set of built-in scalar types, is what we call it. And u32 is unsigned, meaning non-negative 32-bit integer, okay? Next, we can also have something like let num, just num, with i32. Now, i32 can have negative numbers. It's basically the same, and this is actually the default for numbers if you don't specify type. So if I did something like let n1 equals to minus 100, the type for this is by default i32. You can see that Rust rover, so my IDE automatically fills this out for me. If you're on VS Code, you probably won't see that. Next, we have, we can declare temperature. So let's declare temperature. And normally temperature is decimal points, right? So we do that using F64. and we can give a temperature like 36.6. So this is for 64-bit floating point number for decimals, like so. And these are actually just spelling mistakes or like semantical mistakes, so they're not actually errors right here. I'll fix those real quick. All right, next we have booleans. So booleans is pretty simple, simply declare it by giving the type bool. So booleans can only either be true or false. We all know about this. Then we can have something like grade with a variable type of car. So car basically means a single character to represent anything. You cannot have multiple characters like this, so you cannot do ABC like this. It would immediately give you an error. Too many characters in car literal, you can only have a single character. And that's basically pretty much most of the types or almost all of the scalar types that we're going to use in Rust, and you know about them. All of these should be familiar to you. They're just a different syntax. So all you need to do is use a keyword like let, and then give your variable name and give your type by using a colon type equals to whatever number you have. If you don't give a type by default, Rust is actually going to infer that for you, but you ideally want to give types on your own. And let's run the results. So to print out all of these variables, what I can do is I can do something like age and then a placeholder, then temp and then a placeholder for that, then active and a placeholder for that, and grade and a placeholder for that. And we insert all of our variables in the next line or after comma. So the first one should be age, the second one should be temperature, third one is active, and then the fourth one is grade. So all of those errors should go away, and this is how you would print that out. And in my terminal, once again, I'll hit cargo run. So unused variable num, we haven't used this variable, so let me print it out as well. Let me print out num is like so, and then put up a num right here. And then back in my terminal, let me go cargo run, and you can see age 18, temp, active true, grade A, num minus 100, as you expected. Now, aside from scalar types, we also have another type inside Rust, which is called a compound type. So let's give in a semicolon right here, and I'm going to write compound type. What a compound type is it lets you mix different types. So one way we're going to do this is we're going to do a tuple, and next we're going to do an array. So for a tuple, you suppose let person, and person maybe has two different properties, right? One is their name, which is going to be stored in a string, and one is their age, which I'm going to use an unsigned 32-bit integer for. So I can do something like Maya and then give it age of 29. So this is a way I can create a compound variable. So this is basically compounding two different types. One is a string and one is a 32-bit unsigned integer. And I'm assigning the value Maya and 29 to it. So I can access these values by simply while printing. So dash is dash years old. How would I access this Maya and 29 differently? Well, you would simply just do person.0 and person.1. So these are actually indexed. You can infer that from looking at it. So this is in the index position 1, this is in the index position 2. If you added a third variable right here, for example, her salary, like 50,000, you would have to add another type right here, so unsigned 32-bit. And the way you would access the salary as the salary and then do like so, you would access the salary with this index, so it would be person.2. And that is the overall idea of a tuple. It groups values of different types together, accessed with .0, .1, and so on. Next, let's look at arrays. An array is a fixed list size. So let scores, for example, and you give something like this. You give a big bracket, and then the first is going to be the type. So this type is going to apply to every single element or every single component inside this compound type. And next is the size, for example, 3. And then you give in the actual values. So 90, 85, and 100, like so. And this should be a colon, not a semicolon. And there you go. Now you can access these types similarly. So first score is, and you give in a placeholder. And the way you access that is not using dot notation, but using bracket notation like so. So all in all, you have scalars and compound types. Scalar types are pretty obvious. The two that are maybe unique to you are unsigned and signed. So unsigned don't have negative, signed can have negative. And in compound types, we learned about tuples and arrays. So for a tuple, you denote them using small brackets, and inside small brackets, you write the type for every single tuple that you're going to add, and you assign it corresponding to that type. So a string should be a string, and unsigned 32 should be an unsigned 32-bit. So if I try to give this a signed bit, it is going to give me an error because this is supposed to be of the type unsigned 32-bit. And you can access them using 0, 1, 2, and so forth. Whereas an array, you want to make a fixed size of numbers or a fixed size of types, values, and all of those values will have the same type. So all of these are signed 32-bit values, and they are of a fixed size 3. And I can access them by simply using 0, 1, 2, 3, and such. So an array might be a list for you if you're coming from other languages, and tuple is, in most languages, just a tuple. So the indexing for these two will be different. Simply, I'm going to run this, cargo run, and you can see age and everything printed out as is. And you might encounter different situations where you might use different of these types. Next, I'm going to clear all this out once more. So I'll clear everything out and add my main function. We're going to be looking at functions, and functions is pretty simple. So aside from my main, I want a function outside. For example, I want a function called greet, and all this is going to print out is greeting my name. So I want to pass in my name as an argument to this function. So I'll pass in name like so, and inside here, I'm going to print ln. I'm going to write hello, and I'm going to give in my name like such. But why does this give me an error? Well, that's because every parameter inside Rust, so every function that takes a parameter, needs to have a type defined. So this needs to have the type of str defined like so. And now everything is fine. Inside my main, I can call this function, so greet, and then the function name. So the function name is greet, and I need to pass in a name of the type str, so I can write code in like so. And simply, if I run this program, cargo run, I should get hello coded. Simple as that. Next, you can also have functions that return something. So this is something that's very important. Inside this, I'm going to write a function called add, and add is going to take two numbers, right? It's going to take a, which is an i32, and it's going to take a b, which is also an i32. So it's going to take a and b, two different values. Both of them are signed 32-bit integers. And inside here, I'm going to do a plus b. Now, generally, what you would do in other languages is you would do something like return a plus b, and then this a plus b would be returned to the main, and you would print it out from there. But inside Rust, you have to define the return type at the top by simply using this notation. So I'm going to say that an i32 is going to be returned, but it's going to say expected i32 but found null. So it found nothing. When it finds nothing, it's just going to return an empty parenthesis instead of returning null or just faulty values like in other programming languages. And inside here, we actually have to return a and b. Now you'd assume you do return a and b like this, but actually in Rust, all you do is type the keyword a plus b, okay? And I missed a semicolon here, but that's not a mistake. In Rust, any line without a semicolon at the end is an expression. So this is an expression, and its value automatically becomes the return value. So any line where you don't add semicolon like this, if you add a semicolon, it's no longer an expression. So when you add a semicolon, this does not get returned. But at the end, if you don't add a semicolon like this value is the value that's going to be returned from this function. So a semicolon turns this into a statement, and without a semicolon, it turns it to an expression. Let's try adding a semicolon and running this program. So let's try to run add, and let me give two numbers. So let's give 10 and 20. So remember, I need semicolons here as well. Otherwise, this value is going to be returned to main. So always add semicolons at the end, except for when you want to return that value. Right now, I'm using semicolons to show you what goes wrong. So if I do cargo run, it's going to say expected i32, but found nothing. It expected us to return an i32, so a signed 32-bit value. But since this semicolon exists, this is not an expression, this is a statement, so it doesn't get returned. If I simply remove this, then a plus b, which is an i32 value, since we're adding two i32 values to get that, is going to get returned. And if I do cargo run, then that value is going to get returned, and I get hello coded. But since I'm not doing anything with that value, what I can do is I can wrap this around my println, and I can add a placeholder like so. And inside that placeholder, I'm going to add this value. So every time you want to put in any variables, remember you have to use placeholders like this. And I can do cargo run. and we get hello coded and we get 30 as expected. Okay, so yet again, we're going to be tackling another very simple concept in Rust that is inferred from other programming languages, and it's control flow. So simply if-else statements, if you would say so. I'm going to create a number variable here just for testing, and later I'll use this. So a simple if-else statement that I can do is if number mod 2 double equals to 0, then I want to print ln the number is even, and again I can do else print ln the number is odd. So this is actually pretty simple and pretty basic for any programming language, and we get numbers even and numbers odd. All you have to remember is we don't use parentheses here, and after every if statement you need to have a curly brace. So even if you write the print ln in the same line as the if statement, it is still going to be a mistake if you don't wrap it in curly braces. So you always need to wrap it in curly braces like so, and it will work out perfectly fine for you. So you can use this as an expression too. So you can use if statements as an expression like so. So let label, for example, label equals to if number is divisible by 2 equals to 0, then even, else, then odd, like so, and give in a semicolon right here. So notice that this even and this odd don't have a semicolon beside it. That's because if it had a semicolon, it wouldn't get returned. So if number is divisible by 2 and the remainder is 0, then this event even gets returned and the value of label becomes even. Otherwise, odd gets returned and this value becomes odd. So we can simply look at the value right here, print ln, and create a placeholder and print in the value of my label. And cargo run, you can see my label is even. So let's quickly look over loops as well. I'm going to remove these statements and let's look at loops. So the first loop that we're going to be looking at is inside a more like a forever loop. This doesn't really have a name like it does in other programming languages, but I'm going to create a mutable variable called counter. So I'm going to change the value of this counter, and I'm going to let result equals to a loop. So this is how you create a loop. Inside it, I'm going to add a value to the counter. So counter plus equals to 1. So remember, you can do this because counter is a mutable variable. So you can see the value is never read. That's why we get this. Now we're going to read the value. If counter equals to 5, then break counter times 2. And I'll explain why we need this times 2 right here. But I will print ln loop result, and I'm going to print out the value inside the result. So if you run this program inside my terminal, cargo run, we're going to use the value number. Okay, so let's remove this number value and cargo run again. We can see the loop result is 10. So all we're doing here is we're creating a mutable variable counter, and inside, after that, we're creating a variable called result. Inside result, we're looping. We're creating a loop inside result. Inside the loop itself, we're increasing the value of counter until it is 5. If the value of counter has returned 5, we break counter times 2. So the break statement automatically returns the value inside it. Currently, the value of counter is 5, right? So counter equals to 5. So if you do break counter times 2, then it's going to break this loop. It's going to break this loop and then return the value, which is counter times 2, which is 5 times 2, which is 10. So the value of result now becomes 10. And then when we print our loop result, we get 10. So the key takeaway right here is that loop runs forever until and unless you explicitly break like this. And break can carry a value out of the loop, which is exactly what I'm doing here, breaking with counter times 2. Next, we can have a while loop where the condition is at the top. So let mut n equals to 3. So mutable variable n with the value of 3. Remember to put your semicolons. And while n is not equals to 0, then I can do something. So always use curly braces. I'm going to print ln the value of n. So I'm going to print the value of n like so, and n minus equals to 1. So I'm pretty sure you're familiar with while loops by now. This is just a different syntax. Again, we don't use small parentheses here, and we use curly braces here. And print ln lift off. So if I print right here, if I run this program, you can see loop result 10 from the very top. Then we get 3, 2, 1 lift off. So while keeps this loop running as long as this condition holds. So it was 3 once, then n minus equals to 1 made it 2. Then again, this statement running made it 1. Lastly, the statement running made this statement false. So our while loop exited and we got this print ln. We can also loop over a range and an array. So this is one of the most important things that you need to do in programming languages, which is looping over range. So the easier loops in any language obviously are the for loops and the while loops. This is like a for loop and this is like a while loop, but you need to also be able to loop over ranges and arrays. So the way we do that is for I in 1 ... 4. I'm going to print ln the range of I. Now what we get right here, let's look at it. If I cargo run, you can see that this for loop simply just printed out 1, 2, and 3. Automatically for I in 1 to 4 prints out all the numbers starting from the first one and right ending before the last one. It's as simple as that. It's almost like in Python. Next, you can loop over an array. So you can loop over an array like this. Let scores equals to, let me create an array, 90, 85, and 100, like so. And for score in scores, I can simply just print ln score is, and then print that score out. So it's pretty simple to any other programming language. We define an array right here. And let's score for score in scores, it's simply just going to loop through every item of that array once. So once it becomes 90, value of score is 90, the value of score becomes 85, and the value of score becomes 100. And every time the value changes, we're going to print out the statement. So if you run this program, we're going to get score is 90, score is 85, and score is 100 because it loops through every one of those. So that was all for loops. It was all pretty simple and pretty self-explanatory. Nothing really fancy going on over here. Aside from maybe the small syntax of for, everything else should feel pretty familiar to you, and except this loop special statement that we have inside Rust. Let's look at some ownership. I'm going to create S1, which is a string from hello. So this is basically, all this is going to do is create a heap allocated growable string different from the percentage string that we saw earlier. So this is going to create a heap allocated growing string. Next, we can do let S2 equals to S1, right? Now let's try to access this string, so the value of this string, using the initial variable that we created. So print ln exclamation mark and create a placeholder and use S1. So just so that we don't get any errors, I'm going to copy this down and print it using S2 as well. So let's try to run this and see what we get. There it is. It says value borrowed here after move. S1 isn't just a copy sitting alongside S2. Ownership of that heap data that we created, so ownership of this heap data, is physically transferred to S2 as soon as we do S2 equals to S1. S1 is now no longer valid and Rust refuses to let me use it. This is the compiler preventing a whole category of bug where two variables, S1 and S2, both think that they have access to this memory. They are both trying to free and change this memory, but inside Rust, as soon as you assign this memory to any other variable, this variable is the only one who can actually access this memory now. S1 is now redundant. One way we can get around this, or one way that we can fix this, is simply by creating a clone. A clone is going to create an identical copy of that memory. So the way to do that is simply just write s1.clone. So now S2 also has a heap allocated growing string, but it's different from the heap allocated growing string of S1. If I change S2, it has no effect over S1, and I can use both of these independently. So now I can do print ln, and I can go S1 equals to a placeholder and S2 equals to a placeholder, and print out S1 and S2. And if I run this, you will see that both of them contain the string hello, but the one inside S2 is a copy of S1. If I change the one inside S2, it doesn't affect it. So if I actually want a full independent copy, I call .clone that explicitly duplicates the heap data. So now both S1 and S2 are valid owners of their own copy. Rust makes that cost visible instead of actually hiding it like other languages. Let's remove all of this and look at references. So let S1 equals to string from float. So exactly the same what we did. This is a owned string created inside our main function. Okay. Let len equals to calculate length, and we're going to pass a reference by doing %s1. Now calculate length is going to be a function that we're going to create right here, and inside the function it's going to take s, which is a string, and it's going to return a u size. And inside it, simply all we're going to return is s.len, which is the length of that string, which is of the type usize, as you would have guessed. And also over here, you don't add a semicolon because you want to return this statement. Inside here, what I can do now is I can print len. Let's remove all of this and look at references. So let s1 equals to string from float. So exactly the same what we did. This is a owned string created inside our main function, okay? Let len equals to calculate length, and we're going to pass a reference by doing percentage s1. Now calculate length is going to be a function that we're going to create right here, and inside the function it's going to take s, which is a string, and it's going to return a usize. And inside it, simply all we're going to return is s.len, which is the length of that string, which is of the type usize, as you would have guessed. And also over here, you don't add a semicolon because you want to return this statement. Inside here, what I can do now is I can print len, and the length of, just to make it look a little bit pretty, is so and so. So length of s1 is len. So I pass s1 as a reference into the function instead of the value s1 itself. Inside calculate length, the parameter is of the type ampersand string, a borrowed string, because we only borrowed it. S1 is still valid back in the main after the call. We didn't actually move any memory, we just borrowed its value for a while. So let's run it, cargo run, and we can see that we get the length of hello is 5. Now what if we didn't use the ampersands, and what if we directly passed in this s1 reference? Over here, we're going to take in a string. What that does is it moves the value, right? Since we passed the s1 value to this function, now this function is the viable owner of this s1 variable. And you can see that we can no longer access it inside the main. So we can no longer print it or do anything with it because this value has been moved. Value is trying to be used after moved, and the value was moved when we did this. So to prevent that, simply just pass a reference, and to pass a reference, simply just add a ampersand like so, when you just need to borrow it for a little bit. Next, let's look at another example, again of the same thing. Let mute s. This time our string is mutable from hello. This time we've created a mutable string. I'm going to let r1 equals to mute s, and r2 also equals to mute s. And at the very end, I'm going to print len, and I'm going to print these two values, so r1 and r2. If I go into the terminal and cargo run, I should see cannot borrow. This is exactly the rule from the slide enforced for real. Only one mutable reference at a time. This is Rust stopping a data trace. This is Rust stopping a data race before your program ever runs, not after it corrupts something in production. So we can see that we used a first mutable borrow, and then we try to borrow that mutable again at the second time. So this is a mistake. The way you fix this is instead of just borrowing it, you give the references non-overlapping scopes and use it properly through a function. So right after this, instead of doing all of this junk, I'll clean it out and create a function, add exclamation, or actually call a function, add exclamation, and then pass a reference. So mute s, and I'm going to create this function, and it's going to be I'm just going to name it text for now, and we can do text.push str and exclamation at the end. Now when I print ln with a placeholder and the value s, if I go into my terminal, I should see an exclamation added to the very end. So this is a cleaner pattern. We pass a single mutable borrow into a function that needs to change the value. All push str does is it mutates the string in place through the reference without taking any ownership. So through this reference itself, it can change the value without taking ownership, without moving it, just a temporary exclusive write access. And as you can see, when we run it, we get that extra exclamation mark at the end. And the length of, just to make it look a little bit pretty, is so and so. So length of s1 is len. So I pass s1 as a reference into the function instead of the value s1 itself. Inside calculate length, the parameter is of the type ampersand string, a borrowed string, because we only borrowed it. S1 is still valid back in the main after the call. We didn't actually move any memory. We just borrowed its value for a while. So let's run it, cargo run, and we can see that we get the length of hello is 5. Now, what if we didn't use the ampersands, and what if we directly passed in this S1 reference? Over here, we're going to take in a string. What that does is it moves the value, right? Since we passed the S1 value to this function, now this function is the viable owner of this S1 variable. And you can see that we can no longer access it inside the main. So we can no longer print it or do anything with it because this value has been moved. Value is trying to be used after moved, and the value was moved when we did this. So to prevent that, simply just pass a reference, and to pass a reference, simply just add a ampersand like so, when you just need to borrow it for a little bit. Next, let's look at another example, again of the same thing. Let mute s. This time our string is mutable from hello. This time we've created a mutable string. I'm going to let r1 equals to mute s and r2 also equals to mute s. And at the very end, I'm going to print ln, and I'm going to print these two values, so r1 and r2. If I go into the terminal and cargo run, I should see cannot borrow. This is exactly the rule from the slide enforced for real. Only one mutable reference at a time. This is Rust stopping a data trace. This is Rust stopping a data race before your program ever runs, not after it corrupts something in production. So you can see that we used a first mutable borrow, and then we try to borrow that mutable again at the second time. So this is a mistake. The way you fix this is instead of just borrowing it, you give the references non-overlapping scopes and use it properly through a function. So right after this, instead of doing all of this junk, I'll clean it out and create a function, add exclamation, or actually call a function, add exclamation, and then pass a reference. So mute s, and I'm going to create this function, and it's going to be of, I'm just going to name it text for now. And we can do text.push str and exclamation at the end. Now, when I print ln with a placeholder and the value s, if I go into my terminal, I should see an exclamation added to the very end. So this is a cleaner pattern. We pass a single mutable borrow into a function that needs to change the value. All push str does is it mutates the string in place through the reference without taking any ownership. So through this reference itself, it can change the value without taking ownership, without moving it, just a temporary exclusive write access. And as you can see, when we run it, we get that extra exclamation mark at the end. All right, time for structs. All we're going to do at the very top is I'm going to add this statement, derive debug. It is just to auto-generate. It is to auto-generate debug printing support for structs. Okay, so I'm going to create a struct called user. And inside user, I'm going to have username, which is of the type string. I'm going to have age, which is unsigned 32-bit integer. And I'm going to have active, which is a Boolean value. And I'm going to have a comma right here. Inside my main function, I'm going to create a new user. So let user1 equals to user. And the username is going to be string from Coden. I'm going to have its age 29 and active to true. At the very end, I'm going to print ln, and I'm going to use a special colon question mark for the debug placeholder, and I'm going to print user1. Line by line, struct user is a struct group. A struct group relates grouped data together under one type with named fields. So all of these data have different types, but the user itself has only one type, which is user itself. So different fields can be added inside here. The derive debug above it, it's basically an attribute asking Rust to auto-generate the ability to print this struct for debugging. Usually we can't do that. So the colon question mark that we have right here is the debug format placeholder needed because structs don't print with plain curly braces by default. So we're going to run this simply by going cargo run, and then you can see user right here with username Coden, age 29 and active to true. So we can access individual fields inside the struct by simply going inside right here and using user1 username, and we can add another field. So instead of using question mark right here, you can say dash is dash years old. So our placeholders. And the first placeholder is going to have user1.username, which is going to access this field right here. And the second one, user1.age, is going to access this field right here. And once we run this, so cargo run, we can see that we get Coden is 29 years old. We use dot syntax. As you can see, we use dot syntax to reach into individual fields, which is mostly the same for a lot of languages. Also, you're getting this warning because we actually never use the active field. So, and is, we can at the end put user1 dot active to print that out as well. And we should be rid of that error because we've used everything. So Rust makes it absolutely necessary or warns you every time you're not using a variable because that's just an extra space in memory taking for no reason. Another thing that you can do is you can attach a method to a struct using IMPL. So we're going to use IMPL and we have our user right here and we can add a function like so. So a function might be describe, which takes in a reference of self and returns a string. So it takes a reference of itself and then returns a string. I'm going to format this string and I'm going to return dash and then I'm going to say active and then another placeholder and I'm going to do self.username. I'm going to pass in self.active. So whatever user is running this describe method. So if user1 is going to run this describe method, then a reference of itself is going to be passed as an argument. So the struct itself is going to be passed as an argument. And now we can access it by using self.username, like how we did user1.username. But it does that automatically for you. So inside main, you can call it right here. Let's try to call it println. And we need a placeholder. And we're going to call in user1.describe. Since describe is a method attached to user1 using the IMPL keyword, this describe method automatically takes in its reference. So you don't need to actually pass it in. It automatically takes in a reference of itself, which is user1. And inside it, it's going to format this string and then provide it to us. And this formatted string is going to be replaced in this placeholder. Formatted string has self.username, so user1.username, and self.active, which is user1.active. And if we run it, you can clearly see that both of those fields are being used like so. So this is how you can attach methods to your structs. So structs, if you're coming from JavaScript, is pretty similar to how objects work. You create a class, so you can create a class, and you can create objects using that class. So creating this is like an object creating from that class, and you can attach methods to that class that all of the objects inherit. So it's pretty similar to object-oriented programming, and our terminal is so at the end of this section. All right, let's look at some enums and pattern matching. I'm going to create an enum at the very top of this code. So I'll come to the beginning right here, and enum, I'm going to create a traffic light. So what can a traffic light have? It's either going to be red, it's either going to be yellow, or it's going to be green. So all of these basically are variants without any data. So enum is, this is an enum, exactly one of these variants at a time. Enum can only hold one of these variants at a time. So inside my main, I can create a variable, so let light equals to, and use this enum, traffic light. And it can only ever be one of these three. So for example, it's red. Create a traffic light red. And I can match this light. So match light. If traffic light red, if it's red, then I want to print ln stop, right? And I can copy this down a bunch of times if it's yellow, and if it's green, I actually need to remove a space right here. And if it's yellow, then it's going to say slow down. And if it's green, it's going to say go. So simple as that. Enum traffic light. So to recap again, enum is defining a type that can be exactly one of these several named variants. It can only be one of these. Match, so we're going to create a new variable having only one of these values. All match does is it compares a value against each possible pattern and runs the matching arm. So it's going to compare the value of light if it's traffic light red. So light is indeed traffic light red, so the matching arm for that is printing stop, so it's going to print stop. It's going to compare light to our condition, which is traffic light yellow, which is false, so it's not going to print the matching arm. And similarly, it's not going to print the matching arm for this either. So if I go into my terminal and do cargo run, then we should see stop at the very end. Yellow and green haven't been used, that's why we're not seeing this, but we got stop at the very end right here. And there is a property called exhaustiveness. That means basically if you ignore to write any of the conditions. So if we ignore to write or account for the traffic light being green, in the enum, we've explicitly put in red, yellow, and green as variants. And light is using an enum and we're matching light. So there's a very strong possibility that light might be green, right? But inside this condition or inside this statement, if we're not checking for that condition, so we're not checking if the light is green, that means we're going to get an error if the light was actually green. So Rust actually prevents us from doing that. Simply if we do cargo run, then we get the error not covered. The matched value is of the type traffic light. Ensure that all possible cases are being handled by adding a matching arm with wildcard pattern or explicit pattern as shown. So all of our conditions must be met. The compiler won't let me forget a case. No silently falling through a case. No surprise bug 3 months from now when someone adds a new variant and forgets to handle it later on. So let's put this arm back. This right side is known as the matching arm, and let's run it again. And we indeed get stop. So these were variants without actual data. So red, yellow, green didn't actually have any data. They were just variants that we checked against light. You can also have enum with variants. So for example, shape, right? Shape of a circle, and it's going to have the value of a float 64, or a rectangle. So rectangle might have the value float 64, comma float 64. So one for breadth, one for length. And when you go ahead and create a shape, you can create a shape like so. So let C equals to shape, and I'm going to create a circle. But this time it expects a parameter. Earlier, red was just red. It didn't expect anything. It was just a variant. But this variant has a value. So this circle must have a float 64 value assigned to it, like 2.0. Or let R equals to a rectangle. So this is going to be of the shape rectangle. And this expects two float 64 values. So like 3.0 and 4.0. Now we can create functions. Let's create a function that actually calculates the area for these. So let's create a single function to do it. You can create two different functions. So one function might calculate the area for circle and one function might calculate the area for rectangle. But the advantage of using enum is that one function alone can handle both of these. So create a function, area, and it's going to take in shape. So shape is the name, but it's going to take the data type shape itself. So it's going to take this enum shape. It's always going to take an enum shape. So it's not going to take anything else. And it's going to return me with a float 64 value, which is basically the area. Now inside here, I can match the shape. So I can match the shape if it is a circle or a rectangle. So if it is a circle and has a radius, if it is a circle with a radius, then all I want to do is I want to do 3.14 times radius times radius. And I'm not going to add in a semicolon because that would prevent it from returning. I'm going to leave it as such. Again, I'm going to copy this down, and instead of a circle this time, this is going to be a rectangle. So if the shape is of a rectangle, it's not going to have a radius, it's going to have a width, and it's going to have a height. All I'm going to do is multiply the width with the height. And we don't need this 3.14. You can ignore this, and voila. So you can manage your enums like this so that one function alone, so this area function alone, can handle both my circle and both my rectangle. Inside it, it checks the shape, it matches the case, and runs the matching arm. So under here, I can run this from my main. So I can do println, and I can say circle area was, and I can call the function area, and simply just pass in my shape, which is C. Again, I can do the same for my rectangle. So rectangle area was as such. Now remember, after this, you really cannot use the value of this C anywhere. So if you try to print ln and then use a placeholder value to print out the C, remember you cannot do this because you passed in, you moved it. If you hover over this, it says value used after being moved because you already moved this value right here. If you didn't want to move that value, you want to add an ampersand right here and you want to add an ampersand right here. So this would prevent the value from being moved, but you can see we get an error right here. Let me put in right there as well. So that prevents the value from being moved so that you can use it later on like this. Also, you need a display So you have to implement a display method to actually be able to print it out like so. By default, you cannot print it out. That's why to print out enums, you needed this question mark right here, and you need to add that debug. So you need to derive that debug inside the enum and add this question mark. I told you before that you cannot really look inside an enum like this. So you cannot look inside an enum like this without those special statements. But now if we run this program, cargo run, we should be able to see circle area is 12.56, rectangle area is 12, and the stop from earlier. So hopefully all of this is making sense and all of this is coming to you, where to use this ampersands to pass in a reference, where to actually move in your variables, and you should know that you cannot print out or look at an enum directly without having that debug line. So something else that you can do is maybe I have a bunch of shapes. So I have maybe 500 different shapes and I don't want to keep track of all of them. So what you can do is you can have a default condition. So basically an underscore that leads to 0.0. So that means if both of these cases fail, then at the end, we just return the area as 0.0. Now, if you hover over this is going to say unreachable pattern because obviously we have circle and rectangle as two shapes only. For example, if we had a trapezoid and inside a trapezoid, I don't know what trapezoids have, maybe like a float 64 and another float 64 and another float 64. So 3 float 64s. And over here, we created a trapezoid like let t equals to shape. And we created a trapezoid with 1.0, comma 2.0, comma 3.0 right there. And while printing it, we try to print out the area of the trapezoid. So trapezoidal area. Inside our area function itself or the method itself, we're not actually accounting for a condition where the shape is a trapezoid. So we don't know what to do if a shape is a trapezoid. Well, if we didn't have this condition, it would simply fail. This condition would simply fail because we're not accounting for all conditions. But when we have this is going to take in any other case aside from these two. And if that case exists, it's simply just going to return 0.0. So our trapezoid should return 0.0. And like, so it does. It just returns 0 and that's it. All right, now let's look at option, result, and error handling. So inside my main function, actually, before we do that, I'm going to create another function. I'm going to create a function called find user, which is going to take in a user ID of unsigned 32-bit, and it's going to return us with something called option wrapped around in a string. Inside here, if our ID equals to 1, then I want to return sum. So we'll talk about what sum is. I'm going to return a string from called coded. So if our ID is 1, I'm going to return coded. Else, I'm just going to return none. And that's it. Inside my main function, I'm going to let result equals to, and I'm going to find a user with the ID of 1. I'm going to match my result. I'm going to match my result with some name. And I'm going to print ln found placeholder name. Else, if it's none, then I'm going to print ln no user found. And this is pretty simple. So find user, all this find user method is doing is it returns option string, either sum with a name or none. So option string has two outcomes. It's either going to return sum with something inside it. So in this case, a string. It's either going to, the option is either going to return sum with a string inside it. So if you're returning anything except a string, you would have to put like U32 here, maybe if you're returning U32, but we're returning a string. Or it has the possibility of returning none. And inside our main function itself, we're handling it with a match. So always handling it with a match forces me to write code for both possibilities. I physically cannot forget not found case. I physically cannot forget this case because if I don't add this case, my match result is going to give me an error. I have to write this case. So let result is going to call this function with an ID. If the ID is 1, then we're going to get something in return. We're going to get a name or a string in return. So in our match result, this case will be matched. This case is matched and we get the name and we print out found name. If, for example, we printed out 2, actually, let's run this example first. So cargo run, it's going to say found coded, right? But if we passed in 2, now this should specifically fail because there is no user ID with 2. We haven't handled that condition. So it should pass out a none. When it passes out a none, our match result matches this line and gives us no user found. So instead of failing completely, it says no user found so that we're handling all of our edge cases without actually breaking anything. But even so in this case, for example, if you were dividing with a number, just having none would not be sufficient. If you were making an API request you probably want at the end to get why it is wrong or why something went wrong. You want a message, right? So to do that, let's create a function right here. We're going to use result. So we're going to create a function called divide, and it's going to take in two float64 values. So I'm going to take one float64 value, and it's going to take in another float64 value, and it's going to return a result. It's going to return a result which has a float64 and a string. So earlier when we had an option, the option would simply return the data type right here. Inside here, we're using the sum keyword if we had something, or it would return none if we had nothing. But with results, you can actually send two different things. And one of those things explicitly has to be the error message. So if b equals to 0 0.0, so if we're trying to divide by 0, we're going to throw an error. And the error is going to be string from, and I'm going to say cannot divide by 0. Okay? Next, else, I'm going to send in OK and A divided by B. As simple as that. So if everything goes right, this condition occurs where I get the float64 value. If anything goes wrong, then this goes in as my string. Okay? And how do we check this inside here? Well, we can create variables like this, but I'll do it directly. So I'll do match. Instead of creating a variable, I'll directly call it right here. So 10.0 and 2.0. I'm going to match these two. So 10 divided by 2 should be given to this function. If the function has returned OK with a value, so if this condition matches, then this arm should be executed. So we should simply just print ln, the result is, and then print out our value, right? If we get an error, it is going to give us in the form of E, and this is going to be of string. We're going to simply print that error. So print ln error, and then that E. Simple as that. We're going to semicolon right there. Next, we're going to run the same thing. We're going to run the exact same match case, but instead this time we're going to divide by 0 and then look at the error. Actually, these should be commas. That is my bad. And let's run this. So we get the result is 5, and in the second one, we get error cannot divide by 0. So when you have errors, you likely want that error to be displayed. So using result, whenever you have a result that is successful, this first value is going to be returned. So a float64 is going to be returned. Right here, we got an OK, and we got the float64 value returned. Whenever we have an error, we simply type the keyword ERR, and anything inside it is the only thing that's going to be returned through a string. Instead of earlier returning two different things using options, this is much better for error handling. This is the same shape as option, but result carries error details. It has OK for success, ERR for failure, and the compiler makes sure that both of these are handled at the call site. And hash maps. So inside my main function, at the very beginning, what I'm going to do is I'm going to create a growable list. So let mute scores. So I'm going to create a scores of vector I32, vec new. And inside scores, I can push. So scores.push 90, scores.push 85, and as such. So what am I actually doing here? Vec I32 is a growable list. Unlike the fixed size array from earlier, so we got let mute ARR1, for example. Inside this, what we did was we created a fixed size array, so of the type I32, and then we had a size of, for example, 3. And inside this, we had 90, 85, 86, 100, like so. So this is what we did earlier to create an array, right? But this array is fixed. Even though it's mutable, the size is actually fixed. You can only have 3 numbers inside it. But instead, in this case, we got a vector. So vec I32 is creating a new vector with a growable list. And every time that we use the dot push method on it, dot push adds to the end. Notice that I'm going to loop with scores, borrowing the vector to read it instead of taking the ownership. So I'm going to loop through scores for score in scores. And instead of actually taking in the entire scores variable itself, which would replace the ownership, I'm going to take in a reference. And inside the reference, I'm going to simply use that to print the score. So print ln score is score like so. Also, I can only access, so scores, a certain position that I want to access. I do it the same way like I did in arrays. So first score, if I wanted to access this first value that we pushed right here, I can access it using scores and then my bracket notation like so. So when I loop with scores, I'm borrowing the vector to read it instead of taking ownership. So I can still use scores afterward like this. If I wasn't borrowing it, if I would just use it like so, this has transferred ownership and then the value was moved, I cannot use it. Always, when you just want to read it and do something, instead of transferring ownership, always just borrow the value like this. And quickly on this topic, I want to show you the difference between percentage, ampersand string, and string in normal. So let owned be a data type of string, and I'm going to create a memory string from, and it's going to have hello inside it, right? And let borrowed be of the type ampersand str and just have the word world inside it. And I'm going to print ln 1 and then 2 owned and then borrowed like so. Let me go into my terminal. Before, let's look at the score is 95, score is 85, and then the first score is 90. So all of this works. I can loop through my array like I did before by simply using references to that array. But inside here, I got hello world. So string, they seem to do the same thing, but this string right here is owned, growable, and lives in the heap memory. Whereas ampersand string right here is a borrowed view into string data, often a literal like word, baked right into the program itself. You'll use ampersand str for reading stuff, and you'll use string when you need to own or build your own text. Next, let's learn how to use hash maps. So at the very beginning, I need to import my hash map. So use std collections, and I'm going to import hash map. So I'm bringing it from the standard library import. I'm importing in the hash map, and let me create a new mutable variable called ages. Mute ages, and this is going to be of the type hashmap string and u32 mix. Okay, and we're going to create a new hashmap like so, like we did earlier. Now, like earlier, we did push, but inside hash maps, you have to use insert. So ages.insert, and we're creating our own string, basically inserting a key value pair. So from coded and the age of, let's say, 29. Similarly, you can insert something else, let's say coded academy and the age of 49. So we used std collections hashmap, which basically pulls hashmap in from Rust standard library. We use .insert to insert a key value pair. Next, we can get it using if. Let's do a loop if let sum age equals to ages.get coded. And after we get that age, I simply want to print ln coded is age. What we're doing here is .get, like we saw earlier, returns an option. So we looked at an option because keys inside hash maps may sometimes not exist, which is exactly why if we handle it with if let, .get returns an option because key might not exist, which is exactly why we handle it with if let. Tying back to what we just learned, iterating with ampersand ages right here. So for name and age in ampersand ages, so we can iterate through our hash map like this, and we can print out those iterations. So dash is dash years old. So name is age years old. So iterating with ampersand ages is borrowing, again, same pattern as the vec. Also, another note is that in hash maps, iteration order isn't guaranteed. You're going to iterate through every single element, but the order isn't guaranteed like an array. So cargo run, you get coding is 29, coding is 29, and academy is 49. Let's look at some traits and generics inside Rust. So for example, inside my main function, actually before my main function, I'm going to create another function called largest. So inside my largest function, I'm going to take in a list. And this list is going to be a slice of reference, a reference of slice of another list that has a bunch of signed 32-bit values. And it is going to return another 32-bit signed value. Inside it, I'm going to create a mutable variable called largest at the list position of 0. So by default, the position of 0, so list position 0 is going to be the largest value. If I have a list like this, for example, maybe 30, 40, 80, 20. By default, when I look at only 30, 30 is the largest value that we've encountered so far. When I encounter 40, I'm going to replace it with 30. When I encounter 80, I'm going to replace it with 40. But when I encounter 20, I'm just going to keep that 80 value. The reason why we need to take the first index like this is because what if this array was 80, 20, 40, 10? So in this case, the first value is the largest, and when we compare it to the rest of them, none of them are larger, so it remains as is and we get the correct answer. So that is how looping through to get the largest number in an array works. So for a reference of an item in list. So for every item in list, if our item is largest, if our item that we got right now is greater than our largest item, then largest equals to our item. Else we're just going to return largest. Okay, so this is looping through every item inside that list, and if any item is greater than our current largest item, we're going to replace our item with that largest item. So if we have 40, 20, 10, and 80, so it's going to loop through this list. It's going to look at 40 greater than 40. Well, false. It's going to go again. Is 20 greater than 40? False. It's 10 greater than 40? False. Is 80 greater than 40? Yes, it is. So now our largest value is now 80. It's now that item. So that's how that works, and we're returning an I32 value. Now inside our main, I'm going to let numbers equals to a vec. So I'm going to create a vec of a growing number list. So 25, 3, 47, 8. Next, I'm going to print ln, and I'm going to print the largest number is whatever our largest number returns. So the largest list with a reference of numbers itself. Since I don't want to transfer the ownership, I'm just passing a reference to our numbers list or our numbers vec to our function. And if we run this, so cargo run, you can see that the largest number is indeed 47 inside this list. This is the non-generic version. It only works for I32. It's a board slice, which is a view into our vec or an array. So we can make this generic. Generic means maybe instead of 10, 25 like this, I want to pass in characters, and I want those characters to also be sorted alphabetically, or I want to get the largest character looking at the alphabet. So if I passed in A, B, and Z, I should get Z. Well, I can do that by creating this function or remodeling this function to be generic. So before our parameters, I'm going to create a placeholder called T. T is a generic, and it's going to be bounded by something called partial ord, and it's going to create a copy. Inside the list, instead of taking an I32, it's going to take in this placeholder that we created called T, and return, instead of passing in a I32, it's going to pass in another T. Now inside here, everything else remains the same. But the only difference now is that when I copy this line down, and instead of my vecs being just I32s, if I come in here and pass some characters, so maybe A, B, C, and Z like so, and if I run it, actually I should name this cars just to reduce some confusion, cars to reduce confusion. And in my terminal, I can see that that exact same number now works generically, which means it works for Z as well. What is actually going on over here? I know I just typed this out, but basically T partial order dot copy. T is now our generic placeholder. Instead of I32, we're passing in T, and then we're taking out T. The part after the colon is called a trait bound. It says T can be of any type as long as it supports ordering comparisons and copying. The same function now works for numbers and for characters. We can also create custom traits. So this was a trait that is built into Rust, which means that if it can be ordered, and if a copy can be made, then it's T. Another trait that we can use is creating our own. So to create your own trait, what I'm going to do here is I'm actually going to clear all of this out and add our main function. And at the top, I'm going to create a trait called summary. And fn, I'm going to call the function summarize. It's going to take in a copy of itself or a reference of itself, and it's going to return a string. We don't have a body here. It just required signature. For now, just follow along. Next, we can create a struct. Let's create a struct called article. And this has a headline of string. Let's create another struct called a tweet. And this has a text of string. Now we can implement functions into these structs, right? We've learned how to implement functions for these structs. You can do impl, and then you can write the name of that struct, and then you can add a function. But since we have our own method right here, so if we have our own custom trait right here, what we can do is implement summary. We're implementing summary for our article. And inside here, we have to add our implemented item, which is summarize, which is going to take self and return string. Now inside here, we have to actually add the body. What we're going to do is we're going to format article and then self.headline. So we can do the same thing, summary for, instead of article, we can do it for tweet. And instead of self.headline, it's going to give self.text. So now inside our main function, right, we can create objects using the struct. So let article equals to an article with the headline of string from, let's say, Rust hits 1.0. And similarly, we can create a tweet using our tweet struct using, let's say, just learned traits. And since this doesn't have a headline, this has a text, you have to pass in text. But now what we can do is, while printing it out, we can do article.summarize, and we can also do text.summarize. Oh, not text, we can also do tweet.summarize. So these two are totally different types, right? This is a different struct and this is a different struct, but they're called through the exact method name. Both of them have a method called summarize attached to them because they both honor the same trait, and the trait that we created was summary. They both have the same trait, so that this trait can be implemented for both of these structs. So I can implement this trait for both of these structs, and I can change how the method inside the trait works for each struct. The trait gives me, or the method inside the trait gives me article with self.headline for our article, and article self.text for our tweet, or rather this should be tweet itself, so that now instead of every time that we want the text inside here, we don't need to know if there's a headline inside or if there's a text inside. We simply just call the summarize method, and the summarize method already knows what to look for. Now we can do cargo run, and we can see that article Rust hits 1.0 and tweet is just learned traits. Now this might be a little bit complicated or hectic to do if you're doing it for the first time, or if you're doing it for a very small example like this, because right here it would be much easier for us to just get this headline and get this text directly by simply just doing article.text and then formatting it right over here. But what if you want this formatting, for example, like 100 times throughout your code? Then it's much easier to implement an interface that looks like this into your program. So this is the interface idea that we got from the slide that we created in real life. Look at what you just did. You went from a blank screen to hello Rust, to variables, types, functions, and control flow, straight through the two ideas that scare people most, ownership and borrowing, and out the other side into structs, enums, option and result, real collections, and traits and generics. That's the intermediate core of Rust. You have it now. If this got you unstuck on Rust, subscribe. There's a lot more coming, and see you in the next one.